Are you yeah, there's double.
That, that work.
So yeah, are you able to hear now?
I can hear from your microphone, but it's quite echoey.
Oh, it's echoing. But we have turned off the mic from James' laptop, so I hope now it's audible now.
Okay, yeah, try that.
Is that working a bit better?
Yeah, that's better. Thank you.
Great. So I won't touch anything, so hopefully it will stay live and you can hear everything okay. So I was just introducing, if you didn't hear online, that I'm part of the Science and Technologies of Robotics in Medicine, or STORM Lab. And it's led by Professor Pietro Baldastri, and we have a number of academics, postdocs, and a lot of PhD students in the lab at the moment, some of which are my students and some of which are from kind of the other academics in the group. And most of the work I'm going to present is either from those students primarily, or from previous students that have sort of now finished and graduated and moved on to bigger and better things. So I have to just acknowledge, obviously, they put a lot of the hard work into this. I'm just sort of presenting things for now. All right, let's see. Okay, so starting off by a bit of a consideration around soft continuum robotics. So what does this kind of mean? How do we classify it? What are some of the distinctions we might be interested in? So starting from traditional robotics, if you like, at the top here, this is in the context of surgical robotics, so they're already quite unique in many ways compared to your standard, let's say, industrial robots of old. But here we have rigid structures, we have joints, we might have prismatic motion, for example, but basically we're kind of constrained with the rigid mechanical properties of that system on how we can actually perform or create a device that can perform a procedure. These are amazing, the way they've been engineered. They can perform very precise operations and tasks that are sort of beyond, let's say, the normal skill of a surgeon. It sort of augments beyond their own capability. But there are some limitations. They're obviously complex systems. There's lots of components. They don't necessarily always last that long, some of the tools that are on there. And they don't always conform that well to the anatomical spaces that you might want to work in. So they don't flex and bend if you need to curve around the corner or do something around a piece of anatomy that's delicate or doesn't want to be interfered with. You can struggle to do that with kind of rigid tools in this way. So continuum robotics is sort of one of the next steps in the direction. So moving away from kind of rigid links with joints towards kind of a continuous curving structure. So if we have an elastic backbone in our robotic structure, which you can perhaps see on some of these examples here, we can then actuate that in different ways, and we'll come on to some of those. The traditional, perhaps early platforms tend to use things like tendons to drive the system. So by kind of pulling on a tendon through that structure, it will cause it to bend and form this continuous curve, which is quite useful when we consider how analogous this is to some of the pathways we might want to take when we're inside the body, for example. It gives us a nice compact footprint for our robotic manipulators and can reduce kind of the complexity of the assembly and potentially the cost of that structure. And this has really been taken to perhaps another level with the introduction of soft robotics or soft continuum robotics in this particular talk we're thinking about. And that's where we actually use soft compliant materials to make that structure, to make the elastic backbone. So ideally we can make it with fully soft materials so that it has properties that are similar to biological tissues, for example. So it's a lot more analogous to sort of organic material or biological systems in that way. But fundamentally, it will work in similar ways. So under actuation, through different means, we still get that kind of bending into continuous curves. But we now have a system that's even softer and potentially more safe, arguably, compared to other systems. So sort of summarizing what happens as we move from this traditional rigid robotics approach through towards continuum robotics and soft robotics, we potentially can reduce cost and complexity of our assemblies. We can increase the flexibility, the dexterity of those systems. Possibly, we lose some things in terms of how much force we can generate, and that's important if we're trying to do specific tasks with our robot designs. And there is this benefit that's often quoted around safety. So if we use these soft systems, are they inherently safe? It's perhaps hard to justify that that's fully the case at this stage still, but you would definitely think that kind of logically, if we're using a material that's more similar to the properties of tissues, we're less likely to inadvertently damage it during interaction. So hopefully you can see that these different approaches might have some useful clinical applications, but just to, I guess, highlight potentially where they might be used and some of the areas that we consider through the research that goes on in the lab. Looking just at cancer, for example, there's still millions of deaths every year from this, and many of these kind of areas where we find deadly cancer occurs in anatomy that is hard to reach. It's hard to work within, especially if we're looking at a minimally invasive approach. So instead of cutting someone open to try and access these tissues, if we try to go through natural orifices or small incisions, it can be difficult to get to the target that we're interested in, using especially straight, rigid, or inflexible tools. So we look at lots of different applications to suit this, and you can see some of them highlighted here around kind of our cardiovascular system, gastrointestinal tract, and neurovascular as well. So I'm going to go through a couple of, let's say, scenarios or clinical scenarios to try and highlight that potentially, and you may or may not agree, but potentially soft and continuum robotics could be a good candidate for designing a medical system or device or robot that could actually serve the purposes of those clinical applications. So I'll start with gastroscopy. And Manish obviously knows this one quite well. So we worked together on a project in this area, which I'll talk a little bit about through here. But generally, the idea here is that we want to insert the tool into the stomach of the patient, so down the esophagus into the stomach, and be able to visually inspect and potentially take samples within that domain, within that anatomy, so we can diagnose things like cancer or treat many other conditions. So if we were to consider this perhaps from an engineering perspective, we can think we need relatively long tools. We need to have, well, ideally we can go as small as we want, but we can tolerate diameters for this anatomy up to around about a centimeter or so. We need to have quite high range of motion because we need to visually inspect that whole volume. And that's actually kind of something that needs to happen in a fairly open environment. So that's quite important to consider. So sometimes we're in a quite constrained lumen, for example, but in this case, we're partially in a lumen and then partially in an open volume. And we also need to be able to integrate our functional components, our cameras, light sources, and so on. So that puts a certain burden on our design to try and achieve that. So that's one possible application. But if we contrast that perhaps with something that might seem relatively similar on the face of it in bronchoscopy, which is the inspection of the lungs, we'll see that there are actually some different requirements now, and that might lean us towards considering which are appropriate actuation strategies to use through our soft continuum robot designs. So here we can tolerate a slightly shorter tool. We don't need to reach quite as far potentially into the body, but we do need to have quite small diameters because our bronchial tree will branch down and down, get smaller and smaller, softer and softer. So we need to kind of match that anatomy or be able to access it. So if we have too large of a tool, we might be able to insert into the bronchial tree, but we can only reach to a certain extent, and then we would get stuck or wouldn't be able to progress any farther. We need to have quite high precision in this case. So previously we could tolerate quite an open inspection just to look around the stomach, for example. But here we need to be able to select specific pathways to navigate to a location of interest. Let's say if we've picked something up on a preoperative scan that needs to be sampled. So that's an important consideration. And if we need to actually take samples, then we're considering how we're going to do that using potentially catheters, either directly integrated into our system or through some exchange process. And that could then be used to deliver out biopsy or whichever sampling method we need to take to do our diagnosis or potentially deliver treatment. So there's lots of anatomical variation in this scenario, more so than before, and that's both within the same patient and within different patients. Our kind of clinical task delivery is all needs to be done at quite small scales, especially if we're considering deep parts of the lungs. And obviously we have to think about our respiratory motion, which can be quite extreme in this case. So our heartbeat, our lung motions, they need to potentially be compensated for to allow us to precisely navigate to the region that we're interested in. So hopefully you can see the differences in those cases. And we'll just finish with a final one, just to highlight again, a change of scale and a change of application. So this would be intravascular intervention. So again, another area where it's quite popular to see soft and continuum robotics in here, but thinking about kind of what this means in terms of our requirements for the system can be quite helpful. I think normally these would play, but there we go. So these are quite nice animations I didn't do. They're from somewhere else. So, but they're quite useful in sort of showing some of the challenges around this kind of vascular navigation using our guide wires and catheters, which is a very common way to do these kind of things. So if we need to access things within the vasculature, and that can be because there are things like aneurysms or bulges in the vessels, there can be blockages, or there can be a need for doing treatment to alleviate certain conditions. Common approaches are to use these sort of passive pre-bent catheters and guide wires in different sequences in order to access the region that we're interested in, deploy our therapy, which could be things like coils, sort of shown at the bottom here. This has challenges because we might have to reach quite a long way to actually get to the site that we're interested in. We need to work at very small scales, so on the low end of millimeters, sometimes even sub-millimeter, to reach the actual vessels that we're interested in and where that problem might be residing. We have kind of strange requirements around the range of motion. It can be quite subtle and relatively straightforward to get all the way nearly to the vasculature, and then all of a sudden you can have very convoluted vessels that you need to navigate through at the end, or you need to have some level of manipulation close to the target site to get precise delivery of your therapy. And obviously there's lots of tools that have been developed around this in terms of things like balloons and stents, different procedural workflows in order to actually achieve the clinical goal. And so systems may need to be able to handle working with those differences. So hopefully from that, you can see that even though the anatomy is broadly the same in terms of we need to navigate these kind of convoluted pathways, there are quite different challenges depending on where we're looking at as an application within the body. And we can kind of mirror that with the different approaches that we perhaps see for our, I'll get the right slide, for our actuation strategies. So as I kind of briefly mentioned before, we can go all the way from our sort of continuum robotics with, let's say, hard components in its construction, all the way through to fully soft materials, and we can actuate those in different ways. So I'll show some examples here just to give an idea of the diversity of design within continuum robotics. But just to highlight, these are really ones from my research interests and area. And there are actually many other ways that have been proposed in the literature. So this is not to say this is the only way to do it. And especially around things like smart materials, there's lots of new and cool ways to actuate these types of robots. So thinking about mechanical systems as the first option, one of the common methods, as I sort of touched on a bit before, is to use our tendon drive. So we can create structures, we can pass tendons through them and then pull on them with our tension force, or sometimes with a pushing force as well. And that can cause this bending into these usually sort of relatively constant curves. We can create fairly compact structures. We can have quite good force output for these. And we can control them relatively easily because we're just pulling on tendons at the end of the day. So it's not too complex in that sense. But it can be difficult. We still have rigid materials involved. So making them kind of fully soft so that they're inherently safe, as we would like to say, is difficult, and getting them down to the right scales can be challenging because we're trying to route those tendons through and get enough degrees of freedom or degrees of control within the system such that it can do the task that we're interested in. So sometimes other approaches are better. So we have some other options in fluidic actuations. There's a couple of examples here with pneumatic and hydraulic. So here we can create a structure from our elastomer material. So this is a hyperelastic material that will stretch many times its original length. And we can create chambers inside this, or we can design certain structures to basically cause it to change its shape when we inflate it with, or when we actuate it with pressure, either through air pressure or fluid pressure. We don't have to do it like that. We can actually use other strategies, like in this hydraulic case of ejecting fluid from it to actually drive it around, kind of more like a tip-steered robot in that case. But broadly speaking, we can achieve quite high degree of motion, good articulation within these at sort of the millimeter, centimeter scale without too much trouble, and in fully soft materials. And we'll see some examples of that in a little while. But if we want to go smaller than that, it gets quite difficult to do it using fluidics because we have to embed our channels into the structure. We have to connect directly to our robots to be able to pass that pressure or that fluid to the robot itself. And so there are some alternatives which are perhaps more suited to going to smaller scales, and magnetics is arguably the most promising out of those approaches currently. And so this final sort of option is magnetics. And here what we do is we say we can embed magnetically active elements within the soft matrix of that structure. We can magnetize it to have a certain magnetic profile, and then when we apply an external magnetic field to that, it will conform to try and align with that magnetic field, which can cause bending, cause shaping, and we can use it to do things like navigation. So again, we have quite a diverse range of actuation strategies, and they have lots of pros and cons to each of them. And that kind of fits nicely with the different challenges that we see through the different kind of anatomical or clinical use cases that I touched on before. So what I'm going to do now is talk through a couple of examples in terms of case studies. Excuse my very sensitive mouse for some reason. So this is about kind of how we've taken soft continuum robotic designs and picked specific actuation approaches and applied them to given applications, again, to try and meet those requirements and solve a clinical problem. And the first one is from a few years ago now, but is around affordable gastroscopy. And here really the project was about, can we make something that's a very portable, low cost, not necessarily a replacement, but an available option to perform screening in gastric cancer cases or populations where there's potentially a high incidence of gastric cancer, but not the diagnostic kind of capability to screen the population effectively. So we talked already about kind of the requirements for this type of application. And so given the scale of the sort of procedure that we're looking to do, the type of articulation that's needed, that kind of high range of bending, but potentially lower precision, fluidics seemed like the right approach. And so some of the original designs were looking around the use of kind of soft robotic technologies, trying to make them smaller scale, more compact, and suited to the integration of kind of functional components. So these are both projects that Manish and I worked on a long time ago now. But so generally speaking, utilizing soft robotic approaches. So how do we create our internal structures within our device? So this one based on kind of a helical design, and this one more around an origami style design. How do we take those how do we create those internal structures so that it promotes this bending under actuation, ideally at relatively low pressures and ideally at quite high range of motion to suit our needs of looking around the complete stomach. So we can hopefully see, oh, he's moving in a second. Let's try again. Yeah, so these are sort of two examples here. You can see they both have very nice articulation in a 3D workspace, and we can make them down at sort of below the centimeter scale. It does get challenging to make them much, much smaller than that with these kind of complex features because they're fabricated through sort of molding, casting techniques, which have some limitations, generally speaking. So we actually thought about alternative approaches. in parallel to this, and these were actually in parallel to the designs shown in here. But instead of creating kind of a more general soft robot where we have our applied pressure to create our bending, we can actually create an assembly of multiple soft robots, if you like, together in the form of bellows. So you can arrange these bellows segments together in a parallel configuration, which is sort of represented here. And then by actuating those bellows independently to change their length, either increasing or decreasing, you can cause that same level of articulation. And this is broadly speaking what's happening in those soft robotics cases anyway. It's just the nice thing here is by separating those chambers out, you can reduce the pressure that's needed to cause motion, to cause extension or compression. And the other nice thing is that because it works in a bidirectional state, we can either compress or extend our bellows in that case. We can actually create an analogous design for a handle in this case that follows the same kind of kinematics. So here we apply like a multi-backbone styled continuum structure. So this is very much how many continuum robots are built. But we take that structure, which has basically the same kinematics as our parallel bellows. And if we use that to drive our pressure source, so our syringes in this case, as we move the handle around, it will create either kind of vacuum or positive pressure, which is applied directly down to the tip and causes the extension or contraction of our bellows. And you can see it synchronizes really nicely. So we actually can move away from a robotic system as such, and we can create more of a manual handheld device that has this kind of intuitive way of controlling the tip of it without the need for kind of any additional components. This is purely pressure driven. Obviously, it has a camera light source within the tip, but driven by the user itself just by using that handle. And it's sort of proposed that this would be a more user-friendly way of controlling an endoscope. Again, we can make it at relatively small scales down to about 8 millimeters in this current design. And we get the sort of articulation range that we're interested in. So hopefully you can see how fluidics in this case perhaps matches this problem quite nicely, but even within that, there's lots of different ways you can try and solve the same problem, and there are pros and cons to the different approaches. So even here, we have to create quite a complex assembly of parts to make this work, which is not ideal when you think about trying to scale this up to be a low-cost system that can be deployed on scale safely, potentially through kind of single-use designs. So let's move on to the second case study. So this is for a different case, and again, not that big of a change going from, say, gastroscopy to bronchoscopy, but we see that we still saw previously that the challenges, the requirements associated with that are quite different. So here we're looking at magnetic actuation, and that's because we want to be able to reach deep into the lungs. So to be able to provide diagnostic capability and potentially treatment of the peripheral lungs, where at the moment it's quite hard to get that treatment, because in many cases patients will get into a situation where they're under watchful waiting, so they have to just wait and have frequent rescans to check if the condition is progressing at all. It would be nicer if we could diagnose and potentially even treat that more directly and more urgently. So the sort of proposal of this project, which again is now sort of started perhaps 6 years ago or something along those lines, I think, was that potentially utilizing magnetics within soft continuum structures could offer some benefits. It means we can make things smaller, potentially allow us to give the same level, the high articulation, same level of control. But maybe we can make devices that are suitable now to navigate deeper into the body down to sort of the low millimeter scale. So that's sort of the principle of what this was proposed. And how we actually go about achieving this. So the way it was sort of looked at was first around shape forming. So if we can embed specific magnetic elements within the design of our small, soft catheter-like robot, we can hopefully control its shape or its bending direction quite directly. So this is sort of showing the process that we go through to create a shape forming by design tentacle, as we would call it. So here, this is sort of a simulation of what happens if we have 3 magnetic elements in our structure, and these are just consisting of kind of magnetic particles embedded in a soft elastomer matrix. If we give those a specific magnetization, so think of that as the sort of poles of a permanent magnet within the structure, depending on how they're arranged relative to one another, will give us a different shape under the same actuating field. And that's sort of what this is showing. So it's all the different sort of possible combinations for 3 different arrangements of internal magnetic elements. We can take that information and train models such that we can then basically solve the inverse and say, if we have a specific shape that we're interested in, can we predict what the magnetization profile needs to be? So what direction these magnetic elements need to have in their magnetization to give us the equivalent shape. And then we can follow a fabrication process, which is a bit labor intensive here, but I'll talk a little bit about potentially some better strategies later on. Do you have a question?
Yeah.
Yeah.
So with the simulation on your top left,
Yeah.
the middle arrow seems to be changing every time, and the bottom arrow is like changing. What does that show?
So I'll get it running. So these are the magnetization directions of the segments. And so it's kind of going through every permutation. So this isn't, what's happening with my mouse? Right, let me. So here, this isn't kind of like a dynamic simulation. This is just a stacked sequence of quasi-static simulations. So under this configuration, for example, and with the same applied field, you can see these are all roughly in the same alignment with one another. So we get kind of a sort of continuous curve almost, as you might expect. But if we stopped at a different point, it'll let me. We have a different profile now. And so we get a slightly different shape for our structure. So these just represent the different configurations. And this, every time this goes around once, this then increments by 1, and so on and so on. So it's.
This is what's console.
Yes. Yeah. So utilizing COMSOL for its, because it has inbuilt magnetic.
So this segment is fine, but then when you mold that segment,
yeah,
and then you have to magnetize that segment. How do you generally magnetize that part in that direction? Because the magnetizer only does the same line. So how do you?
So
Hiya. How you doing?
So
good, thank you. Enjoying the sun after all that depressing.
Right. So so we utilize this kind of molding process, which let's say was quite labor intensive, but we create our magnetic elements and they don't have a magnetization at that point. But we put some features in them, in this case like pinholes, such that we can align them in a separate mold in a direction that we want. And then we print that mold with the angle that we need for that segment, and then magnetize again using the axial field as mentioned before. And then we can transfer that to the full assembly to then cast everything together, which is very labor intensive, but it's maybe the best way to guarantee that you get the signature that you want. You don't have to do this.
Remain magnetized?
It's a good question. Probably depending on what you do. If you get them close to other magnetic sources, like permanent magnets that we use, it's not great. And they will still remain magnetized, but you may change the magnetization in a way that's not how you or you don't know what it is after that. So you have to be quite careful from that perspective. But generally speaking, they last long enough to be able to test. So the idea of let's say the protocol that would go through would be that they get magnetized and utilized within a short period of time. So it's kind of on-demand manufacture rather than making these and having them on the shelf for a prolonged period of time. Yeah, question?
So in the previous slide, it showed that protection inside the casing, I'm assuming like the magnetized area. So would it be treated like an MRI then, like the patients with like pacemakers and things? Would it affect the magnetic field?
Yeah, so depending on how you create the actuation system, which is somewhat conveniently the next slide. So I guess I'll talk about it here, but you can actuate these in different ways. So the common ways are to use coil-based systems. So by supplying current through some coils, you can generate a magnetic field, which is actually really good because you can switch it on and off just by regulating the current. So you can get very precise control all the way from 0 up to a maximum field, depending on the configuration of the system. Or you can use permanent magnets, which obviously have a magnetic profile that you can't switch off. But the nice thing is that they're generally a bit more efficient because you don't have to obviously supply any current to switch them on. And so you can get quite high output for a relatively small volume of material. So they can be quite beneficial in that sense. You mentioned kind of MRI. Obviously, that's, let's say, the most famous magnetic thing in clinical use, I would say. Although I might be wrong. That has a very high field. So that's more similar to like the magnetizing kind of field. So Teslas in terms of units, whereas for our actuation fields, we tend to look at, say, tens of milliteslas as a maximum. So it's quite a different scale. And if we want to work in systems like MRI systems, there's a lot of more considerations we need to take because it will just remagnetize our magnetic elements. And so we can't really use the same strategies as I showed on the previous slide for sort of shape forming. We have to think about different ways to do it to achieve the same thing. But regarding the, let's say, the potential layout of how this works, it could be done in many different ways. You could have, and people have proposed lots of different options. You can have kind of coil-based systems, which is sort of what this shows on a movable platform. So you can move these coils around to actually actuate the system. You can have permanent magnets on robot arms, which is the approach that primarily we've taken in our lab, which is to mount these bigger robots on the bigger magnets on the robot arms, and then manipulate them within our 3D workspace, generate the field or gradient that we want. And you can create hybrids of these where you have coils that can move, or you have permanent magnets and coils together and do things like that. So there's pretty much, people have thought about every possible combination, and there are some benefits to each of them, and often drawbacks as well. One of the main benefits of doing it with these permanent magnets on robot arms is it gives us the sort of patient scale workspace. So obviously an MRI system is very expensive. It's very involved to install and so on, to get that at a scale that a patient can go inside the system and be imaged, for example. So to do something similar with coils for actuation, you have to have a huge investment in terms of let's say, a bed with coils on or something at that level. It can get very heavy, very expensive, and very power hungry. But if we utilize kind of the benefit of robotic arms to move the magnets around, we can hopefully achieve the kind of workspace that we need to control something within the body, but we don't need to exponentially increase the cost to do so. So it's quite an efficient way to achieve that. But it has a downside. We can't switch them off. So it's potentially, we have to consider safety a bit more in that sense. We can't just cut the power and it switch off the magnetic field. So it will always be on. And obviously, especially if we have a system like this, where we actually use two magnets to give us more control over the field locally, we have to consider how they move relative to one another and how we plan their motions to deliver the type of field that we need, like over time in the sequence. Hopefully that answers it. The question.
What is the maximum distance from which you can control this using the robot?
Do you mean the maximum distance of the
basically, I think
magnets
what
from the
you're
robot?
trying to do is control the catheter inside the lung.
Yeah,
So some patients are high body mass index.
Yeah. no, that's a very fair point. So there are some limitations. Typically in this case, the fields that we need to achieve, which are sort of the low tens of milliteslas, so let's say up to about 20 or 30 millitesla,
Okay.
we're looking at 300 millimeter distance. So it's reasonable for let's say a normal sized average human, but then with this specific configuration, there would be some limitations for larger patients potentially. But you can still scale this. You can use obviously bigger magnets on your robot arms potentially. But then you obviously have to make sure it's still suitable for the robotic system to actually carry that payload, and does increase the safety concerns, but it's not impossible. It's not that difficult in relative terms to do. So if we have quite good control over our field that we're trying to use to control the system, and for the moment we're thinking about just a homogeneous field, so we don't want really variation across the workspace of the robot, so it should just be under kind of torque-based actuation. So it's just that these magnetic elements in the structure are trying to align with our applied field. If we have that kind of dexterity of our applied field, we can add that as a parameter in our sort of optimization. So when we then want to create a specific design for our magnetic elements, we can have the freedom to also change the direction of the applied field. By having those together, we can start to create kind of a sequenced shaping, which is more like follow the leader style motion that we talk about. So there's an example here. So what we do is, instead of just considering it in its sort of full length shape under a specific field, we can think about how's it going to move in these sequences over time or over an insertion distance, such that it should navigate around certain obstacles. So you can see these sort of black obstacles in the video here. And these are the robot arms changing the different fields and hopefully shaping towards that sort of pathway. And you can see some of the challenges with the permanent magnetics there. The transition between fields is problematic. So you sometimes get undesired fields in that case. And there's been, like, one of the PhD students in the group spent quite a lot of time coming up with kind of planning strategies to try and mitigate those issues, so that you have it under control throughout the whole process and not just at these static points. And obviously you can see that they're quite big, heavy objects that are moving around that workspace.
So when the two robots are moving, are you always trying to maintain a uniform field between them?
Depends. So normally in this scenario, for this case, it's assumed that we're at static points. So we're stage one, we're getting this, we want this field, stage two, this field, and we use the kind of just the kinematics of the robot to move to those different positions to give the field. However, with the more advanced planning, there's other strategies which can be things like trying to actually remove the field, so sort of minimizing the applied field whilst transitioning, and then kind of getting back to the field direction that we're interested in. But there are a lot of different ways you can do it, and it's quite an interesting area of robotics if you're into that side of things, but also quite complicated because you need two robot arms, or at least need to simulate them to do it. So can extend that into more anatomically relevant cases. So here, if you take a scan of lungs from a segmented CT scan, for example, you can extract the pathways, and then from those pathways, figure out what the magnetic profile should be for a specific catheter and what the sequential fields would need to be. So you can see in this video, it's not the clearest, but you sort of see the catheter in here, and it's trying to get to this pathway A down here. As we insert, we change the fields by moving the robots again through that step sequence, and it should follow the right pathway to reach that specific one. So this is a slightly more dramatic case, and the sort of tip of the robot is, or tip of the catheter is here. So you see it sort of swing to the other side, and now it should be inserting up this pathway here, again, as we sequence through those fields. So this is taking the same approach, applying it to kind of more human scale anatomy. And we actually did that as well in this piece of work for cadaver lungs. So we segmented scan of some cadaver lungs, did the same process, and then utilized the bronchoscope to deliver our magnetic tentacle, as we call it, into the different pathways. So we segmented out and picked the different pathways. And then we can see that this is sort of the view from the camera of the bronchoscope, it navigating down pathways. And you can see there where it sort of gets to the end of its range, it starts to buckle, which is one of the problems. Yeah.
Yeah, so in this side, you can see soft robotics, we want to reduce the scale, right? We want to always reduce the size. But we have micrometer, nanometer, micrometer, or millimeters. So when you see the scale is over quality, I mean, if in this case we make the soft robotics in nanometer, it looks like over quality. So which side you should think is available or affordable or good size, or which side you should over quality?
It's a really good question, but it's quite hard to say. And I think looking at it from the application requirements is quite important.
Just this application.
Yeah, so if it's just purely to get to a location further in the body, then you could make this much smaller and you probably have suitable performance, provided you can control it such that it doesn't touch the anatomy, because the smaller it is, the lower the stiffness for the same materials. And so if it starts to interact with the anatomy, so if this follow the leader planning isn't perfect, you're going to get buckling problems, and so it's not going to go where you want. Conversely, if you made it very stiff, more towards a traditional catheter, you could almost push it where you want, but then you lose the controllability of it. So you can't actually actively select which direction it's going in. So there's trade-offs. And the other side of it is that if we need to add functionality, so in this case, we wanted to have kind of laser delivery and integrated fiber optic sensing. They have a certain stiffness and mass that you need to integrate in as a payload. And so if you go too small, again, you start to lose the kind of magnetic torques available to be able to control the robot. So it has both, let's say, sort of clinical trade-offs and just limitations, especially with magnetics, as to how much payload you can integrate into your design before it will stop functioning as you intend. If that answers.
Which silicone material we use mostly?
This one is, I think, dragon skin. I don't remember correctly, but it's the sort of standard soft robotics one. So between the high OO range up to the low A range in terms of durometer. So pretty standard stuff. Some people do utilize all the way up to things like PDMS, so a little bit stiffer, maybe even beyond that. But again, you get to a point where using magnetic particles at a maximum concentration, if you go too stiff with the material, your actuation is just not sufficient to really do anything that useful. So yeah, can be a problem. So that's kind of I guess the highest fidelity use case of magnetics in bronchoscopy, or at least a deployment under bronchoscopy to reach hopefully deeper into the lungs. So seems like a good solution generally, but the sort of, I guess, that scenario maybe doesn't highlight directly some of the challenges of using magnetics. And we just talked about a little bit in that answer some of these problems. And so kind of put down here some of the challenges. These are not by any means the only challenges, because there's lots of others in terms of localization and things like that, and control and so on. But in terms of actually making our devices and getting them to do something, assuming we can control them as appropriate, we have to think about how we fabricate it. So we're making things that are very small, and we might want quite variable magnetic properties or even material properties more generally in that structure. But we also need to be able to add other stuff to it, like internal sensors, either for proprioceptive sensing or for actually sensing of the tissue properties, for example. We also have insertion navigation, which I talked about. So if we make our device too small or too soft, how do we kind of overcome the challenges of that low axial stiffness and it buckling under deployment? And how do we compensate things like dynamic motions when going through that insertion, which we haven't done in that example there? And finally, how do we add more functional components to actually do something useful clinically? It's great to get to a point, but how do you actually then do something that's valuable from a clinical perspective? Obviously, you can't solve all of these things at once, but they're important to consider as you go, especially in the context of medical device development, because it's very easy to overlook. And often in sort of soft robotics, sometimes these things aren't thought about, the application's not really over thought about. It's more about, this is a cool way of doing something, this is a cool way of actuating a robot or designing it and so on, which is very valuable. But if we want to actually translate that to a real system, we have to start thinking about some of these problems. So I'm going to go through each of them a little bit, just to highlight some of my thoughts around it and some of the research that we do on this. I won't say too much about fabrication, but this is just to highlight some of the work that's gone on in collaboration with the Future Manufacturing Group that was formerly at Leeds and now at Manchester Metropolitan University, around kind of printing either magnetic materials or the possibility for magnetic materials or integrated sensors onto these soft robots. So there's some examples here I think should play all together. So this utilizes kind of aerosol jet printing, as it's called in this case. Let me go back. Yeah, so utilizes aerosol jet printing to actually deposit both the kind of matrix material, so in this case PDMS base material, and the magnetic material in distributions that we're most interested in. Quite similar to sort of 3D printing technology, but it can be very selective at small scales, which is obviously valuable in some cases, utilizing magnetics. the bottom here, this is the same kind of technology, the sort of aerosol jet printing, but in this case, we can print kind of resistive materials that can then change in resistance as we deform them. So the idea here being that we could print, say, curvature or strain sensors directly onto our soft robotic structure, so we can measure its performance under actuation more directly. Obviously, this is just a general pneumatic gripper, but the principle being that you have the resolution and capability to print directly onto these soft materials, then that could be quite beneficial. And then it's quite exciting process that came from that group around this high resolution self-assembly. So by treating the surface of the material, in this case a substrate like PDMS, with a plasma, very high precision, you can then add polar material. So if you've dissolved your magnetic material, for example, and then it will then self-assemble onto where you've created that kind of region with your plasma treatment. And the bottom example is that applied with magnetic material. So you can sort of see this membrane, really nice features on it under a magnetic field, how that changes its shape. So obviously these are somewhat generic examples, but these are like the underlying enabling technologies that might kind of tick that box in terms of solving the fabrication challenges for more medical-based magnetic robots. In terms of insertion and navigation challenges, so I mentioned about dealing with the compensation of the dynamic motion of the lungs. So this was some work by one of the PhD students in the group around that particular problem. So when you're actually performing these procedures, and you can consider this both from the imaging and also from the procedural perspective, the lungs aren't static. They're not going to have a fixed geometry as such. So during inhalation, exhalation, there's going to be a change in the shape and size of that structure. So from, again, CT scans, it's possible to figure out what that kind of range, that dynamic motion is. And then in this case, created kind of a dynamic phantom, if you like, to replicate those motions. And they can optimize kind of the gating insertion of the structure to try and get it to be able to successfully navigate through that pathway. I think you'll see this one without compensation. So this is just using the previous strategy, but under sort of dynamic lungs. You can see it actually ends up kind of going offline and not being able to navigate. Obviously, this is a slightly not quite analogous to what you would have in the real system, but it's a sort of a trade-off to try and understand some of the, let's say, the characteristics or challenges of dealing with this more dynamic motion. That's one aspect. We can also look at other ways to do that. So potentially utilizing rotational fields. So again, this insertion process, if we want to try and push our robot through the system, it's going to buckle very easily if it's quite soft. So we can use rotating fields here to create this sort of wave motion through our tentacle, and that can break the friction and mean that we can actually use our sort of pushing force to reach much further into the structure. So this has like an oscillatory field of a few hertz applied on top of the robot, and that means that we can then insert it much further in a soft, very small diameter phantom in that case. So that's all, again,
the rotation of those coils you're changing every time.
Yeah, so these are permanent magnets that are spinning. You see the simulation of it here. So the field is sort of rotating around, and that's causing, because of the magnetic profile in the robot, sort of this oscillating behavior, which breaks the contact friction. You can sort of see it oscillating against this soft phantom, and that just stops it from sticking and buckling on the wall. So it's an effective strategy, but it's then hard to implement this with all of the other magnetic control that you want to do. So it's sort of benefits, but also creates some additional complexity. So this is where this interesting approach comes in, and this is really where about this multimodal actuation can potentially look to solve some of these problems. So one of the areas that's quite a hot topic in soft robotics is emerging robots, growing robots, or vine robots, how they might be called. These work in a slightly different way, but effectively you have an inverted tube, so the material sort of passing through itself internally, and if we then pressurize that structure, it will cause the material to get pushed out from inside the structure. That has a really nice property that it means that this kind of effectively grows from its tip, and so there is no relative translation against the external environment. So we don't have to push against it, and then we're not worried about those problems of buckling and so on. So it's really good for navigation in sort of confined, compact environments. But if we just do it with fluidics, which is sort of the traditional way, it's then hard to actually steer or navigate this effectively. So this was proposed by Josh, who's one of the PhD students who's almost finished in the group, to utilize magnetics with Vine robotics. So this is a view of this structure growing. So it's not being pushed. You can sort of see it everting from the tip. But in this case, it's actually being driven by magnetic fluid inside that structure. So it means it's both magnetically active and we can pressurize it to cause the eversion. So this is it now controlled under a magnetic field. So we get both that nice eversion behavior, but also a steerable response under magnetic fields like here. And you'll see in a sec, I think there's obstacle put in place. And so it will deflect around an obstacle. So it maintains that softness that we're interested in.
How is it bending this?
Like an external magnet moving around. So
On the
yeah.
backside.
Yeah, so you can't see it in this frame, but you can sort of see it in this schematic here. But again, so magnetics can solve some of the problems in traditional Vine robots or reverting robots, particularly in medical applications. And Vine robots can solve some of the challenges that we see from traditional magnetic catheters, if you like. So quite a good synergy of having a combined approach. In terms of functionalization, so we want to actually get something at the site and do something with it. We've looked again at potential hybrid strategies to do that. So we don't have that much force with a magnetic catheter, just because of the nature of the amount of material that we can have in it, its stiffness and so on. So here we're looking at kind of locally locking that catheter against the anatomy such that we can then control just the tip of the device at a shorter scale to have better control, precision over its behavior. So hopefully this will show it in action. So this has an integrated balloon structure and a laser fiber in this case, sort of simulating what we might use for our tool. And this is obviously in a brain phantom. So we can deploy the balloon to sort of anchor it against the tissue. This is not a particularly hard anchoring force, but just enough such that we then have a fixed sort of fulcrum point for our magnetic device to be manipulated relative to, which can give us that hopefully improved precision versus just using it as a free moving catheter. We take that potentially a similar approach a bit further. So in this case, we're looking again at multimodal actuation, this time using a tendon to actually create a variable length. So this is for deployment within aneurysm, so we can improve the kind of workspace dexterity of our design. And there've been quite a bit of effort in magnetic catheters to do this kind of thing. So to increase the workspace or the range of motion of your magnetic catheter through different means. So we can add additional magnets to the structure. We can do our shape forming strategy that we've seen previously. We can create uneven distribution of magnetic particles through a structure, or we can even have kind of movable internal magnets within our structure to create kind of a dynamically changeable magnetic profile. So this is perhaps a bit more analogous to that last case, and here we can sort of see an example of 3D printed, it's around 2mm device that's tendon actuated, but we can also control magnetically. So we get quite a nice range of motion in terms of the change in tendon length here.
Is this elastic really?
Yes, yeah, this one. So this is sort of at the limit of printing with that, but you could also cast it with a different silicone material and so on. We combine that with magnetics.
How is this moving up and down? Nitinol wires are that.
Yeah, so it's tendon drive. So on the back end of that, there's a motor that's pushing that drive. So it's, yeah, that has some limitations. It's not ideal, but it is also a technology that is used in catheters already. So sort of cable driven steering. If we combine that length change with our with our magnetic actuation, we can now create kind of quite a different range of workspaces with the same device locally. So if we can anchor this within, say, an aneurysm, we can then kind of reach the different areas that we're interested in. So just to show it in a very simple phantom here, you can see this is like a mock aneurysm of a certain diameter, around 2 centimeters, quite a large one in some respects. We can see here that if we're entering from this perspective, we can articulate this magnetic element around most of the workspace, but also if we have a more complex scenario, we can reach the different regions. So in principle, with more work, we could deploy our coils or kind of therapeutic gel or other materials into place here where we want them with more precision than we might get with a manual current catheter. Okay, so that I think brings me to the end pretty much of the talk. I just wanted to again just highlight that potentially looking at multimodal actuation, which is one of my particular interests through soft and continuum robotics, can start to solve some of the problems that single mode actuation systems have. Obviously, we add complexity because you're dealing with multiple actuation systems and how you deal with the control of that and so on, and still maintain, let's say, low cost, simple to make devices. But I think the benefits so far outweigh some of the limitations. So with that, I'll probably end the talk, but I've added a few points on here of other stuff that's going on, which I can answer questions about if anyone has anything on it. But thank you very much.
So much. It's good. Really amazing. Thank you so much.
No problem.
Since we asked a lot of questions, I thought maybe if there's any questions online, you can type in your questions if you have any. We'll wait for your questions, or if you want to speak up, I'm happy for you to, we can answer your questions. Josh, Babar, if you have any questions, we'll be happy to answer. Meanwhile, if you have any questions in the audience. Oh, there's brilliant.
I've been following on.
Oh, okay. Yeah.
So this is William, he was online, but James, I have to say your talk was so interesting that people have come here to ask the questions.
That's the first.
So William, if you have any questions, please ask.
On the spot. You don't have to if you don't have questions, obviously. But yeah, more than happy if anyone has any thoughts or questions or anything about what I've shown or other ideas that I want to discuss, just let me know.
I think the talk was really interesting, and if there are no questions, we can thank the speaker for such a wonderful talk. And I'll just say thanks to everyone online for attending it. So we'll end it here. Thanks a lot.